In the picture shown, electrical energy is being converted into light energy at a certain rate. Last semester, we learned that power is the rate of energy transfer with respect to time. Power is measured in units of energy over time, or joules per second, and the SI unit of power is the watt. We have seen that the change in electrical potential energy could be written as Q times delta V. I could imagine that if I would divide both sides of this equation by delta t, on the left-hand side of the equal sign, I would have a change in energy over a change in time, which will be units of power. On the right-hand side of the equal sign, I could imagine dividing the term q by delta t. In that case, I would have something that looks like delta q over delta t, which we said previously is a current. The power given off by a device could be written as I times V, the current flowing through that device times the voltage drop across the two ends of that device. Using Ohm's law, V equals IR, we could also write the power as I squared times R or V squared divided by R. These three equations describe the rate of energy dissipated by a resistor or some other device in a circuit that converts electrical energy into another form of energy. An electric heater uses a current of 15 amps and runs a 120 volt power line. If we want to find the power of this heater, we could use P is equal to I times V. If I wanted to, I could solve for the resistance of the heating element using Ohm's law and then use I squared times R or V squared over R, but we already have enough information to find the power of the electric heater. So I would say the power of the heater is given as 15 times 120, and therefore I find the power of this heater is going to be 1800 watts. The second part of this problem asks us to calculate the amount it would cost to run this heater for 3 hours a day for an entire month. We are told that the utility company charges 10.5 cents per kilowatt hour used. The second part of this problem will essentially be a unit conversion, and there are many different possible approaches we can take to solving this part. Before I begin, I would like to point out something about the units of power. 1 watt is 1 joule per second. Power is a quantity that is measured in units of energy over units of time. If I take a quantity that is measured in units of power and I multiply it by a quantity that is measured in units of time, I will get something out that is measured in units of energy, measured in joules. This term here, kilowatt hour, is a power multiplied by a time. So the cost of energy from the utility company is going to be 10.5 cents per some unit of energy that we could presumably calculate. 1 kilowatt is 1000 watts, and 1 hour is 3600 seconds. The way I am actually going to go about solving this problem is to recognize that the power of my heater is 1800 watts, which is going to be 1.8 kilowatts. So I could say the power of my heater is 1.8 kilowatts. Now, if I look at the cost of energy from the utility company, which is 10.5 cents per kilowatt hour, and I multiply that by the power of my heater, which is 1.8 kilowatts, then I could cancel out the units of kilowatts, and I find that it will cost 18.9 cents per hour to run my heater. Now, if we know it costs 18.9 cents per hour to run my heater, and I run my heater for 90 hours, because we are running it for 3 hours a day for a month, which we'll assume is 30 days, then I could say 18.9 cents per hour times 90 hours implies that it will cost 1701 cents to run my heater for 3 hours a day for an entire month, or $17.01. I would like to conclude by saying what we have demonstrated here is just one possible method for determining the cost it would take to run the heater every day for 3 hours a day for a month. There are other methods that we could have used to come to the same result that would have been just as valid. Another method, for example, could have had us convert this 10.5 cents per kilowatt hour into the cost of energy per joule from the utility company. We then could have calculated how many joules of energy the heater will use if it's run for 3 hours a day for a month, and then use those two pieces of information to determine the total cost it would take to run the heater for 3 hours a day for a month. To finish off this chapter, we will discuss the topic of alternating current, or AC. To motivate the idea of AC, recall Ohm's law, V equals IR. In nearly every scenario encountered, the resistance R was assumed to be constant. If the resistance R is constant, that implies that if the voltage V is going to somehow change with time, then the current I should also change with time. Furthermore, in whatever manner voltage V varies with time, current I will need to vary in sync with the voltage, because again, we are assuming that the resistance R is constant. A very useful and direct application of this idea is to consider a voltage that varies sinusoidally with time. If I could describe the voltage V as a sine wave, and we assume resistance is constant, then I expect that the current I should also be described as a sine function. And I could write I as being equal to I naught times sine of omega t. In this equation, I is the current at a specific instant in time. So I think of I on the left-hand side of the equal sign as being a function of time. I naught is the maximum value of the current. So I will think of I naught as being a constant. All of the time dependence is contained in this sine function. If I were to plot current as a function of time, I would get something that looks like this, with a current that is fluctuating between a maximum value of plus I naught and a minimum value of minus I naught. Now, what do we mean by a positive current or a negative current? If you imagine that you have a very long wire in front of you, then you could declare that current flowing to the right would be described as positive current and current flowing to the left would be described as negative current. That implies that at some times you will have a very strong current flowing to the right, at other times you will have a very strong current flowing to the left, and at other times still you will have no current flowing at all when I is equal to 0. There's also this term omega. Omega could be thought of as a term that determines how rapidly the current switches direction traveling back and forth. In the United States, AC electrical current fluctuates at 60 times a second. This implies that if you were to plug a device into a wall outlet, the current flowing through that device would be switching its direction of travel back and forth at a rate of 60 times a second. If current is going to be a function of time, then we expect power to be a function of time as well, because power is equal to I squared times R, and we are assuming again that R is constant. Therefore, I could write the power output by a device at any one instant in time as being equal to I naught squared sine squared omega t times R. Now, the equation shown here for power is the power at a specific instant in time. We could also meaningfully think about the average power. If I were to plug a device into a wall outlet where the current is fluctuating as a sine wave, and then I record the total amount of energy put out by that device over some long interval of time, and I could divide the total amount of energy given off by that device over that long interval of time, I could meaningfully talk about the average power put out by that device. The average power put out by the device is designated with a bar over the P, and it can be shown to be 1/2 times I naught squared times R. Now, with all of this being said, let us present a question. Suppose we have a device that is connected to an AC source, and this AC source produces a maximum current I naught. This device will have an average power output over a long interval of time of 1/2 times I naught squared times R. Now, suppose we unplug this device from our AC source, and we will connect this device to a DC source, such as a battery. What current will need to flow through this device to produce the same average power output as when this device was connected to an AC source? The current that is flowing through the device when it's connected to a DC source, such that it produces the same average power output, is known as the RMS current. And this RMS current is equal to 1 over the square root of 2 times I naught. Now, if we know what the RMS current is going to be, then we could meaningfully talk about the RMS voltage, because voltage is closely related to current from V equals IR.